We are now discussing the Curry-Howard correspondence between logic on the one hand and programming, simply type lambda calculus, on the other hand. If you felt that our discussion of the terms of the simply typed lambda calculus was very quick, then you are right, we went through it very quickly. But on the other hand, this is justified by the fact that you actually are already very familiar with these constructions, except that you know them under a different name, namely under their logical name. Think of it this way. The types that you have seen so far, think of them as propositions, and the terms that you have seen, think of them as proofs, as inference rules. Specifically, I would like you to understand the following analogy. The zero type that we have seen corresponds to the false proposition in propositional logic. The times construction, A times B, the type A times B, corresponds to the proposition A and B. The arrow construction A arrow B, the function type A arrow B, corresponds to the implication A implies B. And the sum or coproduct type A plus B corresponds to the OR type A or B. The new thing that we have not seen in the world of logic yet are the computation rules. Think of the computation rules of ways to simplify a proof into a proof of the same fact, but that is less complicated. We will now go through the term constructions again. I will scroll back in the slides, and I want to explain to you this the term constructions again, using the knowledge of the propositional logic that you have from the previous parts of the course. So let's go back and let's start with the term construction for the zero type, the empty type. As I said, the zero type is analogous to the false proposition. Remember that for the false proposition we did not give an introduction rule because we said, well, there is not really a proof of the false proposition. This corresponds to the fact that here we don't have an introduction construction for the zero type. The elimination rule for the false proposition said that if we have a proof of false, then we can deduce from that a proof of any proposition. So here we think of x colon 0 as x a proof of the false proposition, and then if C is any proposition, we get a proof of that proposition, and we call that false elimination. In Lean it is called false.elim. And there is no computation rule since there is no introduction rule. Let's go to A times B. The table that I showed earlier said that A times B is analogous to A and B. So let's look at the introduction rule. The introduction rule for A and B said that if we have a proof of A and a proof of B, then we can form a proof of A and B. This is precisely analogous to this introduction rule here, where we can form a term of A and A times B from a term of A and a term of B. The elimination rule for AND said that if we have a proof of A and B, then we can get out of that a proof of A with the elimination rule on the left, and we can get out of that a proof of B with the elimination rule on the right. So AND elimination on the left and AND elimination on the right. These constructions here, T.1 and T.2, are precisely analogous to the elimination on the left and on the right hand side of A and B. As I said, the computation rule we have not yet seen on the side of the logic. This is something that we only discover now when we think about programming with this language. So to repeat, the computation rule says that if we first form a pair, A, B, from ingredients A and B, and then we take what we think of as the first projection of that pair, we get the original A back that we plugged into the pair. And if we form the pair A, B from these individual components and then take the second projection, we get the B out that we plugged in initially. So we can think of A and B as proofs of A and proofs of B, and then we form the pair. We take the first component, the first projection out of this pair, or the second one, and we get the original proofs back. Let's look at implication, or the arrow type. The introduction rule says that the introduction rule for the logical introduction rule for A implies B said that in order to prove that A implies B, it is sufficient to construct a term B of type B, which might depend on a proof of the proposition A. And this is exactly what this introduction rule here says. If we can form an implication or a function from A to B by constructing an element of B, a proof of B, using, whenever we want, a proof or an element or term of A. The elimination rule says that if we have a proof of A implies B, or a function from A to B, and we have an element of the antecedent of this implication, or of the input type of this function, then we can get a proof of the consequent of this implication, or in the programming language, a term of type B, by using this function application or implication elimination. And the computation rule says that if we start with B, which is a proof of B that depends on A, and we have an element of A, then we can recover that B in the sense that we get B back where we have to replace all the occurrences of X by A. And finally, the term constructions for plus, which, as I said, corresponds to or, A or B. Let's look at the introduction rule. If A is a proof of A, then we can form a proof of A or B by taking the left inclusion, in left, from A to A plus B. This corresponds to the or introduction on the left. If we have a proof of B, then we can get a proof of A or B, or a term of A plus B equivalently, by using in right of B, or as we called it in the logical world, OR introduction on the right. The OR elimination rule said that in order to prove that A or B implies C, we need to prove that A implies C, or sorry, we don't need to prove that, but it suffices to prove that A implies C and B implies C. So the elimination construction here corresponds exactly to the OR elimination rule of logic. And then the computation rule says that if we have a proof of A or B, or a function from A plus B to C, and we evaluate it on an element that comes from A, then we get f of that element. And if we have this function f comma g from A to B plus C, and we evaluate it on an element that comes from B, then this function evaluates to g of that element B. This concludes the analogy between the simply typed lambda calculus and logic. And this analogy is summarized on this slide. I will not go through that slide, but I urge you to look at this slide and understand every single line of it. So we have 4 different type constructions, or 4 different logical constructions: false, conjunction, implication, and disjunction. And in each case, the introduction and elimination rules correspond to term constructions in the simply typed lambda calculus. Let's look at some examples. In the first exercise here, I would like you to understand what the type of this lambda term, of this simply typed lambda term is. So the term is the term lambda x in A times B is mapped to x dot 2, x dot 1. I give you some time to think about it. You can also pause the video and think about it for a little longer. Okay, the type of this term is A times B to B times A. How can we deduce that? Well, it's a lambda term, so it must be the type of this term, since this term starts out with a lambda, its type must be a function type. And the input must be A times B, because this is the argument here. This is the type of the input x of this function. Let's see what this function does. So it takes an x and maps it to a pair. This is a pair. So we know that the output is a pair type, has a times. So we just have to understand what goes to the left and to the right of the pair. But if x is of type A times B, then x dot 2 is of type B, according to our rules. So on the left hand side, we get an element in the first component of this pair, we get an element of B. On the right hand side, in the right component, we have x dot 1. Since x is of type A times B, x dot 1, the first projection, is of type A. So to the right of the times symbol here, we get A. Next, we look at the type A plus B implies, or to function type B plus A. Here the task is to write a function of this type. Again, I will give you some time to think about this, and I encourage you to pause the video, think about it, and then restart the video once you have a suggestion for a solution to this exercise. Here is my solution. I suggest the following construction. So this is quite a complicated example. It's important, let's start out with the following observation. We construct a function that is defined on a sum type, on a plus. So we use this construction with the brackets, the case distinction. Yeah? And in order to construct a function from plus, from an OR, it suffices to construct a function from A into the target, B plus A, and separately from B into B plus A. So on the left-hand side of this construction, we need to construct a function from A to B plus A, and on the right-hand side here, we need to construct a function from B to B plus A. Now, how do we construct a function from A to B plus A? Well, this function, it will start with a lambda. We have lambda A in A dot something, and this something should be of type B plus A. But in order to construct a term of type B plus A, when we have at our disposal an element of A, that's easy. That's in right of A. We take this element of A and we consider it as an element here in B plus A, or think of it as B or A. Yeah? So we use, in logical language, we use or introduction on the right. Similarly, for the second function here of type B arrow B plus A, or if you want of type B implies B or A, we can simply say we take our assumption B and we use OR introduction on the left, or in the vocabulary of the simply typed lambda calculus, in left of B to construct a function from B to B plus A. And then finally, when we apply this bracket construction, which is the same as OR elimination, or analogous to OR elimination, to the two functions from A to B plus A and B to B plus A, respectively, this gives a function of type A plus B implies B plus A. It's important to understand, and I encourage you to try this at home, that these constructions that we have here, they correspond to proofs, and you can easily write out these proofs in, for instance, in Lean or as a proof tree, and you will see that these constructions here correspond exactly to proof trees in Lean. Please do this at home. It will be an exercise in one of the problem sheets. Okay, lastly, let's take a look at classical logic. When we discussed propositional logic, we made a big deal of the distinction between intuitionistic logic and classical logic. So why is that? Well, it turns out that the inference rules of classical logic, they do not correspond to anything in the simply typed lambda calculus. If we translate the types or the propositions that occur in the inference rules of classical logic, if we translate them to types in the simply typed lambda calculus, we obtain A plus A arrow 0 in the case of excluded middle, and we obtain A arrow 0, arrow 0, arrow A in the case of double negation elimination. It turns out that in the simply typed lambda calculus, we cannot construct a term of this type for a general A. Similarly, in the simply typed lambda calculus, we cannot construct a term of this type for a general A. This is what we mean when we say that these inference rules of classical logic do not correspond to terms in simply typed lambda calculus. And this is why we generally prefer proofs that do not make use of these inference rules excluded middle and double negation elimination, since these proofs then will not correspond to a term in the simply typed lambda calculus. Let's summarize what we have learned in this series of videos. The simply typed lambda calculus is a core programming language whose type constructions correspond precisely to the logical connectives of propositional logic. So we had the 0, which corresponds to false. We had the times that corresponds to the conjunction. We have the function types that correspond to implication. And we have the coproduct or the sum type that corresponds to disjunction. The term constructions of simply typed lambda calculus correspond precisely to inference rules of intuitionistic propositional logic. The classical rules do not correspond to anything in the simply typed lambda calculus. This concludes our exploration of the simply typed lambda calculus. See you next time.